Hello friends, I am Dr. Nilesh Dani, working as a lecturer at Government Polytechnic Rajkot. We are in the series of lectures for diploma second semester students, and the subject is Advanced Mathematics Group 1 and Group 2. The topic of this lecture is differentiation and its application. In the series, we have discussed about differentiation and its various aspects. Differentiation is very important topic for engineering and technology, as it's applicable widely in the various fields. As you know, we have seen so far differentiation and its definition. It is limit h tends to 0, fx plus h minus fx upon h. We have seen the derivative of some standard functions like x raised to n, e raised to x, a raised to x, log x, sin x, cos x, tan x, cot x, sec x and cosec x. We have also seen that what is working rule for the addition of subtraction, multiplication and division for of the derivative of that function. Also, we have seen that how to get derivative of composite function. It is also known as chain rule, which is derivative of y with respect to x is equal to derivative of y with respect to u into derivative of u with respect to x. It is known as chain rule. Also, we have seen differentiation of implicit function, where directly the equation is differentiated with respect to x and then it is solved for dy by dx, that is derivative of y with respect to x. Also, we have seen differentiation of parametric function, where y is a function of t, x is a function of t, and that derivative is obtained by dy by dt upon dx by dt. Also, we have seen last time logarithmic differentiation. So, we can differentiate the function. Before differentiating the function, we take log both the side and then we differentiate it. It is called logarithmic differentiation. Generally, this type of derivative is used for a function which has variable base and variable power, that is gx raised to hx. Now, let us discuss today about successive differentiation. What is successive differentiation? Let us see first. Successive differentiation is differentiation of a function more than once. Means any function y is equal to fx, we differentiate more than once. Means we differentiate the function 2 times or 3 times or 4 times or in general n times. Here the concept which we use for differentiation and successive differentiation remains same. Means all these concepts which we have seen so far can be used to get the successive derivatives. Now, we know that derivative of y with respect to x is known as dy by dx. If I differentiate dy by dx once again with respect to x, that is d by dx of dy by dx, it is called second order derivative, that is known as d2y by dx2. Similarly, d2y by dx2, if the second order derivative, if we differentiate with respect to x, gives third order derivative, that is d3y by dx3. So this is known as second order derivative, that is d2y by dx2, and this is known as third order derivative, that is d3y by dx3. Second order derivative means we differentiate y which is equal to fx 2 times, and d3y by dx3 means we differentiate y with respect to x 3 times. In general, we can have fourth order derivative, that is derivative of third order derivative d3y by dx3 with respect to x, known as d4y by dx4. Similarly, d5y by dx5 is equal to d by dx, or derivative of y, derivative of x, derivative with respect to x of d4y by dx4, that is fourth order derivative. So this is fourth order derivative, this is fifth order derivative. In general, if I differentiate any function n times, gives nth order derivative. So derivative of n minus 1 order derivative of y with respect to x is known as dny by dxn, and it is known as nth order derivative. Now, as we know that successive differentiation can be differentiated n times, means any function can be differentiated n many times, but as per our curriculum we confined ourselves to second order derivative only. But let us see how the function y is equal to fx can be differentiated more than once. So the function I have taken is y is equal to fx, sin x, and if I differentiate sin x with respect to x, that is dy by dx, is equal to cos x, that is derivative of sin x. Now to get second order derivative, that is d2y by dx2, we differentiate first order derivative, that is cos x with respect to x, gives the second order derivative. So it is d2y by dx2 is d by dx of cos x. Cos x is first order derivative, and that gives minus sin x. So minus sin x is second order derivative of y is equal to sin x. Now this minus sin x, that is second order derivative, can be differentiated with respect to x, will give us third order derivative, that is d3y by dx3 is equal to d by dx of minus sin x. Minus sin x is second order derivative, and that gives minus cos x, that is derivative of sin x is cos x, and minus sign is already there, so it is. So third order derivative of sin x with respect to x is minus cos x. If we differentiate one more time, that is fourth order derivative, that is d4y by dx4 is equal to d by dx of minus cos x. Minus cos x is third order derivative of y with respect to x. So if we differentiate cos x with respect to x, gives sin x, and minus sign is already there, so minus minus plus sin x. So derivative, fourth order derivative of y is equal to sin x is equal to sin x once again. So this is called successive differentiation, and these all derivatives are called successive derivatives. So second order derivatives, third order derivative, fourth order derivative. Similarly, we can have fifth order derivative, sixth order derivative, and so on. But we in this curriculum confined ourselves to only second order derivative. So we'll discuss the second order, means derivative up to order 2, means we differentiate the function y is equal to fx only 2 times to get the successive derivative. Now let us see an example. To get derivative of y is equal to log sin x with respect to x, and also we find second order derivative. So whenever we need higher order derivative, first we must find the single order derivative. So in order to get d2y by dx2, means second order derivative, we must find the first order derivative, that is dy by dx. So let us find out derivative of y with respect to x, that is dy by dx. Here you can see log sin x is a composite function, so we use chain rule, which we have seen earlier. So dy by dx is equal to log x. If we have, then derivative of log x is 1 upon x, but in place of x we have sin x, so it is 1 upon sin x, and in place of x we have sin x, so we multiply by its derivative, so we have d by dx of sin x. Derivative of sin x is cos x, so we have dy by dx is equal to cos x upon sin x, which is equal to cot x, So derivative of y with respect to x is cot x. Now we need second order derivative. So what we'll do here, we differentiate this dy by dx, that is cot x, once again with respect to x. So that will gives us second order derivative of y with respect to x. So for that we have d2y by dx2, that is second order derivative of y with respect to x is derivative of dy by dx, that is cot x with respect to x, and derivative of cot x is minus cos x square x. So derivative of y is equal to log sin x is cot x, and second order derivative, that is d2y by dx2 of this y is equal to log sin x is equal to minus cos x square x. Similarly, we can find third order derivative, fourth order derivative, but as we have seen, that is not in the syllabus of diploma curriculum, so we will not discuss that. Let us take one more example. Here you can see the example is of parametric function. So the given function is parametric function where parameter is theta. Now first we'll get dy by dx. To get dy by dx, we will use differentiation of parametric function, that is dy by d theta upon dx by d theta. So first let us find dy by d theta. So for that, dy by d theta is equal to derivative of cos cube theta is 3 cos square theta into derivative of cos theta. Derivative of x cube is 3x square, but in place of x we have cos theta, so it is 3 cos square theta into, in place of x we have cos theta, so we differentiate by its derivative, that is derivative of cos theta with respect to theta. Here again we are using chain rule. So next step is 3 cos square theta will remain same into derivative of cos theta is minus sin theta. So it will become minus 3 cos square theta into sin theta. Now let us find derivative of x with respect to theta. So dx by d theta is 3 sin theta, sin square theta, because it is sin cube theta. So derivative of x cube is 3x square. So similarly derivative of sin cube is 3 sin square theta into derivative of sin theta, which is cos theta, as we have seen just now for y. So here we are getting derivative of x with respect to theta, that is 3 sin square theta into cos theta. So these are the derivatives of y and x with respect to theta. Now let us get dy by dx. So dy by dx is equal to dy by d theta upon dx by d theta, which we have already seen in derivative of parametric function. Now dy by d theta is minus 3 cos square theta into sin theta, and dx by d theta is 3 sin square theta into cos theta. So if we substitute these two values here, we have minus 3 cos square theta into sin theta divided by 3 sin square theta into cos theta. So here sin theta, cos theta will get cancelled, 3 will get cancelled, so it will be minus cos theta upon sin theta, that is minus cot theta. So dy by dx is equal to minus cot theta. So here we are getting first order derivative of y with respect to x, that is equal to minus cos theta, and the derivative is in terms of theta, not x or y. Alright. So here we differentiate this dy by dx, that is minus cot theta with respect to x, in order to get the required second order derivative. So here, as we know, dy by dx is equal to minus cot theta. Now let us differentiate this with respect to x. That gives second order derivative. Second order derivative of y with respect to x is equal to d by dx of minus cot theta. Here you see that function cot theta is a function of theta, where we are differentiating with respect to x. So again we use chain rule here. So first we'll differentiate this function with respect to theta, and then theta will be differentiated with respect to x. So here we get derivative of minus cot theta with respect to theta into d theta by dx. This is called chain rule, as we have seen in the derivative of composite function. Now derivative of minus cot theta with respect to theta is equal to cosec square theta. So d2y by dx2 is equal to minus cosec square theta, that is the derivative of cot theta. This minus sign we have kept here, so it is minus into minus, that will become plus, into d theta by dx. As we have seen that dx by d theta in the previous slide, we have seen that dx by d theta is 3 sin square theta into cos theta. So we are getting d theta by dx. So reciprocal of this is 1 upon 3 sin square theta into cos theta. So this is the value for d theta by dx. This is the value for d theta by dx, that is 1 upon 3 sin square theta into cos theta. Now this is sin square theta, so 1 upon sin square theta. So here it is minus into minus will be plus cos square theta upon 3 sin square theta into cos theta. Now 1 upon sin square is cosec square theta, so we have cosec square theta, and already cosec square theta is there in the numerator, so it will become cosec raised to 4 theta, and this is 1 upon cos theta, it will become sec theta. So 3 is there in the denominator, so we keep as it is 3 into this is cosec square theta, and this sin square theta, that is 1 upon sin square theta is cosec square. So cosec square into cosec square is cosec raised to 4 theta into 1 upon cos is sec theta. So this is the second order derivative of this function y is equal to cos cube theta and x is equal to sin cube theta. So this is how we can find the second order derivative of parametric function. When the function is parametric, we first find dy by dx using the derivative of parametric function, that is dy by dt upon dx by dt, and after differentiating this function y with respect to x, that is first order derivative, we generally differentiate the function will be in the form of parameter, that is dy by dx. So we differentiate with respect to x, so we use chain rule and we differentiate that derivative, first order derivative, with respect to parameter into parameter with respect to x, that is dt by dx or d theta by dx. This is the way how we can get the second order derivative if the function is given in the parametric form. So whenever we have to find second order derivative, all the rules and concept which we have seen so far, it will be used here. So you should keep all the rules and concept in the mind to get the second order derivative of the function. And let us see the examples for the second order or successive differentiation. Here we are given a function, that is y is equal to a sin mx plus b cos mx, and we are asked to prove that d2y by dx2 plus m square y is equal to 0. So generally we will be given a function in terms of x, and we are asked to prove a result which involves second order derivative, maybe first order derivative, or maybe y. So that equation we have to prove. So in order to prove this equation, that is d2y by dx2 plus m square y is equal to 0, let us differentiate the given function with respect to x first. So let us find dy by dx. So dy by dx is equal to a derivative of sin x is cos x. So derivative of sin mx is cos mx into derivative of mx, because it is composite function. So derivative of mx is m. So it is m plus b into derivative of cos x is minus sin x. So derivative of cos mx is minus sin mx into derivative of mx, that is m. So here we have differentiated this term, that gives a cos mx into m, and differentiated second term, that is b cos mx, it gives b into minus sin mx into m. Now m can be taken common from both this term. So if we take m common, we have m into a cos mx plus b into minus sin mx. Now here we have differentiated directly the dy by dx. So d2y by dx2, here m we have taken here, right? So it is a into m into derivative of cos mx is minus sin mx into m, that is derivative of mx with respect to x, minus, this is plus minus minus, b into this m we have taken here, so it is bm into derivative of sin mx is cos mx into derivative of mx, that is m. So here there is 1m, here there is 1m, so m into m is m square, here also there is an m, here also there is an m into m is m square. So m square is there in both the term. Also we have minus sign here in the first term and second term. So what we can do exactly, we can take m square common here. So here we have minus a sin mx minus b cos. Now this red color font, if we take minus sign common, it will be exactly matched to y. That is, this quantity, these two quantity which we have encircled with ellipse, they are equal. So y is equal to this. So these can be replaced by minus y. So if we write minus y in place of this red color font, we have this is minus y, and if we take minus y m square y on that side, it gives d2y by dx2 plus m square y is equal to 0. So this is y, or minus y rather. So m square into minus y, that is minus m square, and if we take minus m square y on the left hand side, it will become plus m square y. So that what exactly we want to prove. So this way, any function, if we are given and asked to prove this type of relation which involves second order derivative, first order derivative may or may not be, and y may or may not be, then we can prove it in this way. Let us see second example. So the next example, if y is equal to sine log x, then prove that x square d2y by dx2 plus x dy by dx plus y is equal to 0. Now in order to prove this, first we'll find first order derivative, and as we know that sine log x is a composite function, so we must use chain rule in order to get dy by dx. So let us get dy by dx. derivative of sine x is cos x. So derivative of sine log x is cos log x, and in place of x we have log x. So we multiply by its derivative, that is derivative of log x. It is 1 upon x, which is mentioned in the red font. So here it is dy by dx, that is derivative of sine x, that is cos x. So derivative of sine log x is cos log x into derivative of log x is 1 upon x. Now dy by dx, this x, if we take on the opposite side, it becomes x dy by dx. So x dy by dx is equal to cos log x. So this y we have taken on the opposite side, so it is in the denominator here, so it will be in the numerator if we take on opposite side. Now differentiating this equation with respect to x. Here we are having product of two function, that is x into dy by dx. So we use product rule here, that is derivative of product of two function, that is we differentiate first keeping second constant plus differentiation of second keeping first constant. So if we use this, we have x remain as it is into derivative of y with respect to x is d2y by dx2 plus derivative of x with respect to x is 1 into dy by dx as it is. So it is dy by dx. So here we have used product rule. So x is as it is into derivative of y with respect to x plus derivative of x is 1 and dy by dx is as it is. This is equal to derivative of cos log x. Derivative of cos x is minus sin x. So if I take derivative of cos log x, it will become minus sin log x. But log x, in place of x we have log x, so we must differentiate, multiply by the derivative of log x, that is 1 upon x. So here this red color we have mentioned the derivative of log x, where it is due to the chain rule we have applied. Once again this x, if we take on the opposite side, if we multiply the entire equation by x, we have x into x, that is x square, x into x is x square, into x into dy by dx, and this sin log x is y. So this can be replaced by y. This can be replaced by y. So if I replace by y this and multiply the entire equation by x, we have x square d2y by dx2 plus x dy by dx plus this is actually y, but it is minus. So if we take on opposite side, that is left hand side, it will become plus. So it is plus y is equal to 0. So here this, if we multiply entire equation by x, here x into x, that is x square into dy by d2y by dx2 plus here we multiply by x, so it is x dy by dx, and plus here already we are having 1 by x, so that x and x will get cancelled, so we will get minus y. So that minus y we are taking on the left hand side gives plus y. So that exactly what we want to prove. So this way any function given to us and asked to prove the result which involves second order derivative may or may not be a first order derivative, or may or may not be the y, that equation can be proved in this way. Let us have a parametric form of a function. Here a parametric equation is given and we are asked to prove this. Here the function y is equal to 280 and x is equal to 80 square. That is a parametric equation. So exactly we want to show whatever function we are given, whether it is an implicit function or a parametric function or any other type of function, such type of second order derivative and its relation can be established. So let us find first derivative of y with respect to x here. So in order to get derivative of y with respect to x here, we take derivative of y with respect to t and then derivative of x with respect to t. So we have dy by dt first, that is 2a is constant and derivative of t with respect to t is 1. So derivative of y with respect to t is 2a. Similarly, we can get derivative of x with respect to t. It will give dx by dt is equal to derivative of at square with respect to t. Now a is constant, so it remains as it is, and derivative of t square is 2t, so it is 2at. But what is 2at? 2at is nothing but y, so this 2at can be replaced by y. So exactly dx by dt is nothing but y. So this way we have obtained derivative of y with respect to t and derivative of x with respect to t. Now let us get dy by dx. So dy by dx is dy by dt upon dx by dt, as we have seen in the parametric form. So for the differentiation of parametric function, it is obtained by dy by dx is equal to dy by dt upon dx by dt. Now let us substitute the value of dy by dt and dx by dt, that is equal to y, in this equation. So we get dy by dx is equal to here 2a, that is derivative of y with respect to a, divided by dx by dt, that is y here. So we got dy by dx, that is 2a upon y. Now whatever there in the right hand side in the denominator, we take on the opposite side, so that will be in the multiplication. So if we take this y on the opposite side, it will become y into dy by dx is equal to 2a. Y into dy by dx is equal to 2a. Now let us differentiate this equation with respect to x. Now here, as we know, we have product of two function, that is y and another is dy by dx. So we use product rule. We differentiate first keeping another constant plus differentiating second keeping first constant. So y is as it is here into derivative of y with respect to x is d2y by dx2. So y is as it is into derivative of dy by dx with respect to x is d2y by dx2 plus dy by dx. This dy by dx is as it is, so that I have written as a black font, and into derivative of y with respect to x is dy by dx. So in red color we have mentioned derivative of this y with respect to x, keeping these dy by dx common or as it is, right? So we have two dy by dx. One is derivative of this y and another this dy by dx we kept as it is, and derivative of 2a is 0. Derivative of 2a is 0. Now this is dy by dx into dy by dx, so it will become square of this. So we have y into d2y by dx2 plus dy by dx whole square, that is derivative of y with respect to x whole square, is equal to 0. So this way we can prove the result which we exactly want to prove. So whatsoever the function given to us, whether it is an implicit function or a parametric function, or it is differentiated using logarithmic differentiation, or it is a composite function, it doesn't matter, we can find its second order derivative in the same way. Let us take one more example. Here it is y is equal to e raised to x into sin x. And we are asked to prove that d2y by dx2, that is second order derivative of y with respect to x, minus 2 dy by dx plus 2y is equal to 0. Now this example we will prove here. So here y is a product of two functions, that is e raised to x and another is sin x. Now in order to prove this, we first get dy by dx using product rule. So let us solve here. The function given to us is y is equal to e raised to x into sin x. Now if we want to prove the result, we first get dy by dx. dy by dx, that is first order derivative. Now here we are given product of two functions. One is e raised to x, another is sin x. So what exactly we will do, we'll keep one function as it is, that is sin x, into derivative of e raised to x. This is actually derivative of e raised to x. As we know, it is e raised to x. Plus here e raised to x we keep as it is, that is first function, into derivative of second function, that is cos x. That is cos x. So what exactly we have done? We have used product rule. One function is e raised to x, second function is sin x. So second function we have kept as it is, into derivative of first function, that is e raised to x, is e raised to x. First function we have kept as it is, and we have differentiated second function, that is sin x, with respect to x is cos x. Now as we can see that e raised to x into sin x, this e raised to x into sin x is nothing but y, because e raised to x into sin x is y. So this term can be replaced by y. This is derivative of y with respect to x, plus this is e raised to x into cos x. E raised to x into cos x. So this term, which I have marked with rectangular border, is nothing but y. So that we have taken as y. Now what exactly we'll do? We'll differentiate this equation once again with respect to x. So derivative of dy by dx with respect to x gives second order derivative, that is d2y by dx2. That is equal to derivative of y with respect to x, that is derivative of y with respect to x. Again we have product of two function. We keep cos x as it is, into derivative of e raised to x is e raised to x, plus e raised to x as it is, into derivative of cos x is minus sin x. So each time I write the derivative of the function in the parenthesis or a bracket, and the remaining term we write outside. So here once again this is nothing but y, this is nothing but y, and it has minus sign, so that can be written as d2y by dx2 is equal to dy by dx plus cos x into e raised to x, e raised to x into cos x, this term, e raised to x into cos x. Here also we have e raised to x into cos x. So if I substitute the value of e raised to x cos x from this here, I can write dy by dx minus y. This is the value for e raised to x cos x from this equation. It is from this I can write e raised to x into cos x is equal to dy by dx minus y. So this we are using here, plus, or I can say minus because it has minus sign, so it is minus y, so I can write this as minus y. Now dy by dx plus dy by dx is 2 dy by dx, so it is d2y by dx2 minus 2 dy by dx, because this is dy by dx plus dy by dx, so it is 2 times dy by dx, and it has minus plus sign, but if we take on the left hand side it will become minus, and this is minus y, so it is minus 2y, but if we take on the opposite side it will become plus 2y is equal to 0. Exactly this is the equation which we want to prove. So what exactly we have done here? Here we are given product of two functions. One is e raised to x, another is sin x. So we have obtained the first order derivative. Derivative of e raised to x keeping sin x constant, plus derivative of cos x, sin x keeping e raised to x constant. Now this e raised to x into sin x is y. So this we have replaced by y. So whenever you can replace any value by y or dy by dx, you can use that, so that can help you to get the direct equation which we want to prove. Now these we have replaced by y, and these again we have differentiated with respect to x. So d2y by dx2 is first second order derivative of y, that is differentiating dy by dx with respect to x, is equal to, this is y and its derivative is dy by dx, plus here once again product rule is used, so cos x into e raised to x plus e raised to x into minus sin x. Now these e raised to x into cos x can be replaced by the value which we have here, and for this e raised to x cos x we can get the value dy by dx minus y, that is dy by, that we have replaced here in the equation, and this is minus y because it is minus e raised to x sin x, and y is equal to e raised to x into sin x, so it is minus y, so this is minus y. Now dy by dx plus dy by dx is 2 times dy by dx, but if we take on the opposite side it becomes minus 2 dy by dx, plus it is minus y, that is minus 2y, so it is plus 2y is equal to 0. That exactly we want to show, that we can see on the slide that exactly this result we want to prove. This is the result we exactly want to prove. So this is the way in which we can prove the result like this. So whenever we are given any equation or function in y is equal to fx and asked to prove the result which involves second order derivative, first order derivative and y, we can perform the solution in this way. As far as possible, try to substitute the value for y and dy by dx in the process, so you will directly get the solution of the or the result which we want to prove. The second method is you first find dy by dx, then find d2y by dx2 and substitute the value of d2y by dx2, dy by dx and y in this equation, and as a result you will get 0 on the right hand side. That is the another way, but that may be the lengthier or sometimes may be difficult also. But if you don't find any such type of clue from the given function, you can directly substitute the first order derivative, second order derivative, and y in the given equation which you want to prove on the left hand side. You will definitely get the right hand side as a process. So this is also one way to prove the result. Let us see one more example. So y is equal to log of x plus root of x square plus 1. Then we are asked to find 1 plus x square d2y by dx2 plus x dy by dx. So let us solve this equation, example. We are given the function like this. We have y is equal to log x plus root of x square, and we have to prove that 1 plus x square into d2y by dx2 plus x dy by dx is equal to 0. This exactly we want to prove, that 1 plus x square d2y by dx2 plus x dy by dx is equal to 0. Now first we'll find derivative of y with respect to x. So if we want to get derivative of y with respect to x, here we must use chain rule. Derivative of log x is 1 upon x, and here in place of x we have this equation, so we multiply by its derivative. So here we have 1 upon x plus root of x square plus 1 into d by dx of x plus root of x square plus 1. Now this term will remain as it is, that is x plus root of x square plus 1 into derivative of x with respect to x is 1, and derivative of root x is 1 upon 2 root x, so it is 1 upon 2 root of x square plus 1 into derivative of x square plus 1, that is 2x. So this 2 and 2 will get cancelled, and hence we get this is x upon, so 1 upon x plus root of x square plus 1 into this root of x square plus 1 we can take as LCM. This 2 will get cancelled, so it is root of x square plus 1 plus, here x is there, so it is x upon root of x square plus 1. Now these two things, this and this, will get cancelled, so we can cancel it. So it is equal to 1 upon root of x square plus 1. So this is dy by dx. So here we got dy by dx, that is this. Now we will differentiate this function second times, that is d2y, or before that let us multiply this on the opposite side, because it is better to get this on the opposite side because it will be in the multiplication, and we know that here we need 1 plus x square as a multiple of second order derivative. So if we square it, we'll get there. So let us here multiply this root of x square plus 1 on the opposite side. We'll get this. Now if we square it, so if we square it, we have x square plus 1 into dy by dx whole square is equal to 1 square, that is 1. So exactly what we need x square plus 1, so we have taken square, so it is better to differentiate this function. Now let us differentiate. Here we have product of 2, 1 and 2, so we differentiate this keeping this constant and differentiate this keeping this constant. So we keep 1 x square plus 1 constant into derivative of this. It is 2 dy by dx into d2y by dx2. Derivative of x square is 2x, so derivative of this quantity is 2 times dy by dx into derivative of dy by dx with respect to x is second order derivative. So this portion is derivative of this quantity keeping this constant, plus here if we differentiate this with respect to x, we have 2x, derivative of 1 is 0 into dy by dx square is equal to derivative of 1 is 0. Now here dy by dx is there in this term, dy by dx actually square is there, so it is dy by dx into dy by dx, so dy by dx is there here, 2 is here in both the term, so 2 into dy by dx if we take common, it may not be 0 or it cannot be 0 rather, so the remaining term is 0, so the remaining term here is x square plus 1 into d2y by dx2, that is second order derivative, plus this is x dy by dx is equal to 0. So this is exactly what we want to prove. What exactly we have done here? Here dy by dx is there in both the term, so 1 dy by dx we have taken common, and 2 is there in the both term, so 2 we have taken common. 2 into dy by dx cannot be 0, so the remaining term is 0, so x square plus 1 d2y by dx2 plus this is x dy by dx, 1 divided by dx will remain is equal to 0. So this is what exactly we want to prove. So this is how we can get the equation which we want to prove. There are some more example. You can try yourself. This is one of them. You can try it. If I is equal to e raised to x, prove that d2y by dx2 minus cos x dy by dx plus sin x into y is equal to 0. And some more examples are also there. You can prove this also. So this way, if any function is given and we are asked to prove any equation like this, we can prove it. You practice some more example of this type and try to get a command on this. This is second order derivative, and we have proved certain result for that. So this is all about successive differentiation. I hope you will try more examples to get a good command on it. Thank you.